Hey everyone, I'm Codes, and let's explore DFS, maze generation, and Sudoku solving. Now, Sudoku solving and maze generation might sound like two completely different things, but at the heart, the algorithm we can use to solve them is very similar. I also want to preface this video by saying that DFS is in no way the most optimal algorithm to solve these two problems. In fact, it's one of the slowest. It is, however, a very useful algorithm that all coders should know. And I'm kind of proving that by showing you how it can be used in two seemingly completely different problems. Let's start with the algorithm itself. DFS, or depth first search, is a recursion algorithm used to traverse all possible outcomes. In a typical problem that uses DFS, there are some decisions that can be made, and the right set of decisions will lead to the answer. In Sudoku's case, the decision to be made is which number to place in a square. In the maze generation, the decisions is which wall to remove in each square. DFS works by calling itself with a different decision as its parameter. So for example, if we have two possible decisions, then each DFS function will call itself twice, once with decision A being made and the second time with decision B being made. Then once we made all possible decisions, we observe the final game state and see if it works. If it works, we got a solution. Also note that in some cases like maze generation, it doesn't really matter if the solution works. We just want a maze, so in that case we would just grab the final state we get. If we look at the recursion tree of DFS, we can see that it did in fact traverse all possible solutions. Also, I just want to quickly say that DFS, a lot of times it's used for many things, and these two problems that I'm showing you are very specific use cases of DFS. It can be used for pathfinding, it can be used for filling in an area, basically a lot of things, but yeah, these are very specific cases. But yeah, so let's get to the first problem. Maze generation. We will solve this problem with DFS and a stack algorithm. I will link the Wikipedia page describing this algorithm in the description, and I will also link to my website with a live version of the maze generation so you can play around with it. Here's a quick video showcasing this algorithm. The author will also be credited in the description. Alright, so the way we do this is by having the DFS algorithm be called from a cell into a random direction. Notice how instead of doing the usual more than one decision, we're making only one decision here. The decision, however, is a random left, right, top, or bottom decision. And whichever cell we go to, we remove a wall between that cell and the one on which we were before. We also mark that cell as visited, so we never go back to it again. Finally, we push the position of the cell to a stack. Now if we go to a cell with no visited neighbors, and we can't really go to anywhere because all the neighbors are visited and we don't want to go to one that's visited, we will use the stack to backtrack our DFS until we find a cell with again unvisited neighbors, and we will keep doing this until we run out of visited cells. Notice again how the cells with all neighbors visited will become ending paths, as they will have all three walls around them except one. So implementation wise, what I did is just generate all walls in JavaScript and push them to arrays. Then just do what I said just now, and ta-da, we got ourselves a maze. If you would like to see the code or have me explain it, just comment and I'll reply to you. And if enough people comment, I might make a video showcasing the code in detail. If you want to just see the code and try to make sense of it yourself, here's some screenshots. Anyways, now let's move on to Sudoku solving. Okay, so what I want you to do right now is pause the video and tell me how you would do it using a similar strategy, DFS and a stack. Alright, the Sudoku solver I wrote in C++, so I will link the GitHub repo in the description. Also, yeah, so how do we do it? Well, we'll start with an empty cell, or we'll start with all the empty cells being 0, and the ones with numbers are just those numbers. So we have like a 2D array of integers. Zeros means the input cell was empty and we have to fill it. And we also need three functions that return to us a bool, basically telling us if we can put a certain number in that cell. Okay, one function is for rows, and one for columns, and one for squares. Basically, these three functions will check if a certain number appears anywhere else in the puzzle. If yes, return false. So for example, if the row function will, it will be called with like that number, and if we'll find that number in a certain row, will return false. And these functions will be useful in our DFS. So now let's start our DFS on the top left cell. We will increment the cell from 0 until all those functions return true. So we'll have a while loop while that cell goes up to 9. If all functions return true, we break out. This way we know we found a potential number. Then we go to the next cell and do the same, making sure we keep all the cells we go to in a stack. Okay, now imagine this. One of those numbers might have worked, but it's not the answer. And the cell we are on is already at number 9 and still nothing works, right? We messed up. The while loop never quits. Or it does quit, but we didn't find an answer. So what we do is now we make the cell 0 and then go back through the stack that we used to the previous cell and repeat this process. So we increment the previous cell and we do it again up until that cell is 9. We keep checking it. If it works, then keep going. If it doesn't work, make it 0. Again, go back. This works. So if you think about it like high level, if you think about it, at first it'll go for the minimal solution. Like it'll try to make everything 1, and it'll tune itself, right? The while loop, it's sort of like the algorithm is sort of tuning the puzzle until it finds one that works. If the stack reaches the size of 0 and we're trying to go back, so it didn't work, then it means that the puzzle has no solution, and you can just output no solution if that's the case. Here's some screenshots of the code. If you want it explained, just comment that you do. But yeah, that's mostly it. Okay, so those are some DFS implementations. Again, they're very specific problems, and the DFS used in those problems is it's modified. It uses a stack. It's kind of different. Actually, if you want to do some research yourself, a problem that is a really good one at like showing how DFS works is actually the bucket fill tool problem, kind of. So if you ever use the bucket fill in Paint, that's kind of how DFS works. If you guys want to do some research on your own, just do that. Research setup. It's a good visual representation, and if you guys have any other questions, just post them in the comments and I'll try to answer. If you have any suggestions regarding the pace of the video or the content, also just comment it. Yeah, thanks for watching, and I'll see you guys later.